Good afternoon, grade 11s. Welcome to the show. You tuned in this hour with myself, Deborah Precious, and Mr. John. We will be doing mathematics, Euclidean Geometry, which is maths paper 3. Now, before we continue with the lesson, just a quick reminder, don't forget to post all your questions, your queries, and your comments on facebook.com/learnextra or mindsetlearn/live. I'd be waiting here, and I'd love to hear about you guys. For now, though, enjoy the lesson.
Taboko, thank you so much. Just a little correction. Guys, we know that because we're doing caps in grade 11, it's no longer paper 3. This is core stuff. This is stuff that's not optional. So the grade 12s, if you're watching, hey guys, this is your paper 3 stuff. So I hope there's some grade 12s out there that are taking note that might be doing paper 3. But for grade 11s, it's all part of what you have to know. Now, I'm standing in because the regular presenter, Dina, is just delayed a few minutes. So I'm going to kick the lesson off. Then we're going to play tag team. Is that cool?
No problem.
And Dina's going to come in and she's going to do the really hard stuff. So I'm just going to chat to you a little bit about Euclidean geometry and tell you what the lessons, what's coming up in the lesson. We'll do a little bit of revision of grade 8, 9, and 10 geometry. And then we'll talk about today's topic, which is all about circles. So let's get going. And here we go. So Euclidean geometry. Now, if you were watching the grade 10 lessons, and I hope you get a turn to do that, to watch some of the earlier lessons if you're in grade 11, don't forget the basics are taught in grade 10. So if you get a chance, you would have seen we were doing coordinate geometry. So this is different. This is Euclidean geometry. It's named after a man called Euclid, and he did a whole lot of geometry without measuring. It was all about thinking and proving and deducing what the right answers were. And he started off by making some assumptions, and then he built on those assumptions and didn't bother to measure, but just reason things out. That's what Euclidean geometry is about. It's about getting together a collection of knowledge, ideas, and putting them together, building up a framework so that we can argue and show whether something is really real or not. So Euclid started with some things called axioms, but we're not going to get into that. We're going to say to ourselves, let's take a look at what we're going to focus on this afternoon. The thing we're going to focus on is we're going to work with 3 theorems in circle geometry. The 3 theorems are the angle at the center, something about the diameter, and the angles in the same segment. Now, those are all about circle geometry. But as I was saying to you, Euclid built up this basis of knowledge, starting with some assumptions, some ideas, and then he added to them and built on those. Now, in your learning so far, you've built up a whole lot of knowledge about geometry. I want to revise some of those things because they're going to be important in solving these things called theorems. Theorems are just things that we can say, these are true. We've been able to prove them. So imagine it like this. If we can prove that A equals B, and then we can prove that B equals C, then we can say that A equals C. And so we carry on. We build on things. And to get our understanding of these theorems, a theorem is just something that we accept because it has been proved true. It's an argument, much like our legal system. When lawyers go and the parliamentarians make the laws, and then they go and argue a case in court, and the judge creates a precedent. The next lawyer can come along and say, but hold on, that judge said that. So the same must apply in this case. So we build on the knowledge. We build up our understanding. So let's do some building. And the first thing that we're going to start with is to talk about ideas about lines. We're not dealing with circles yet. We're going to talk about lines, parallel lines, and triangles. Now, guys, this takes you back, some of you back to primary school, where you would have cut triangles out, you would have done patterns, and you've done a whole lot of stuff. But there's some important principles here that you need to know. And you're going to need to remember these, because these become tools so that you can state them as reasons why you are saying certain things when we come to do geometry type questions. So let's start with them and let's recognize what we're dealing with. When we deal with straight lines, and just by the way, the notes this afternoon, which Teboch has given you the short link to download, they've got the summary for you. I would suggest you copy it, you write it down, you put it up over your bed, and you recite it every time you go before you go to sleep. So you can remember these things. You must know them. Some of them you do know. So let's look at the first one. Adjacent angles on a straight line. So the diagram here shows you adjacent angles. Let's measure. That's line A, B, C. It's a straight line. We've got a line that intersects with that, which is DB. Now the adjacent angles are angle 1 and 2. They're not equal, but notice that they're next to each other. I'm just going to highlight that one in pink, and this one, which is angle 2, I'll highlight in blue. Now adjacent angles on a straight line, what do we know about them? We know that they add up to 180 degrees. We can say that these are supplementary. They add up to 180 degrees. The terminology of Euclidean geometry is to say angles that add up to 180 degrees are supplementary. So the reference that we use is ADJ. That means adjacent, shortening of adjacent. Angles, this little symbol means angles, and a straight line, STR, and line. So whenever you want to refer to this fact that adjacent angles on a straight line are supplementary, they add up to 180 degrees, you just simply write this little reference down. ADJ, angles, straight line. That will give you a weapon to argue if you want to say something about things being on a straight line and they're adding up to 180. Quickly, let's move on. Another important theorem. This can be proved, it can be shown to be true, but now we can accept it. We don't have to go and prove it all over again in the reasoning of our argument. We can take this as building block number 2, dealing with straight lines. We can say two straight lines intersect, then they form vertically opposite angles. So let me illustrate these. So we've got the straight line. I'm just going to highlight the lines for you so that you can see they're standing out. There's the yellow one, AB. And let's do another one, the blue one, CD. And I'm just putting them on top of each other. And what I'm wanting you to see is that this angle here, which is angle E4, is the same size. It's vertically opposite angle 2. Angle 4 and angle 2 are opposite each other, vertically opposite, and they're equal to each other. Can you see that in addition, angle 1 and angle 3 are vertically opposite? So they don't have to be vertically opposite only in the vertical plane. They can be vertically opposite in the horizontal plane as well. Now guys, very quickly, I want to deal with parallel lines. Oh, I've forgotten. Very quickly, the reference is vert opposite angles. Vert op angles. So if you want to refer to the fact that they're vertically opposite, we must just write down vert opposite angles. Now, parallel lines, very quickly. We're just going to go through parallel lines. And there are 3 or 4 things you need to know about angles between parallel lines. The first one is we have corresponding angles. And I'm just going to not go through the whole definition. I'm going to say this line here is parallel to that line, and we have a transversal. That means another straight line that cuts that line. Let's just draw it in over here like that. The pink one is not parallel. I've shown the green ones are parallel by putting arrows on the end of them. We're saying that the ones that are corresponding are on the same side of the transversal, and notice they're both below the parallel lines. So they're in the same relative position. In this case, they're on the right-hand side of the pink line, and they're below the parallel lines, each of those. We say these are corresponding angles. And the reference, if we got this, is we say corresponding angles are equal. If we ever want to use it, that's the trick. That's the referencing in our argument. We kind of use it as, well, Mr. So-and-so said it. Well, we're saying Euclid said corresponding angle. We don't have to say Euclid said. We can say we know it's true because corresponding angles are equal. Now, the next one. In the same way, we've got something called alternate angles. Now, alternate angles are between parallel lines. I hope you can see the parallel lines here. I'm going to highlight them in yellow. So I'm just going to put the highlight there. That's a parallel line. And the second one that is parallel to it, and I'm just going over it just so it will stand out. The transversal in this case, I'm just going to draw in freehand, is that pink one. Now notice here, they're not on the left and the right. I mean, they're not on the same side of the transversal. The one angle is on the left side of the transversal. So P1 is on the left, whereas Q1 is on the right. You'll also notice that P1 is below the yellow line and Q1 is above. That's what we mean by alternate angles. They're not corresponding, they're not in the same position, they're in the opposite position. They're in the alternate position. So when we reference this, we're going to say alt angles equal. Last one, or second to last one that I want to deal with, is co-interior angles. Okay, so co-interior angles tells us, here's our parallel lines again, and here we go. There's another set. Those are the two parallel lines. Let me just mark them in as being parallel. That's parallel. Now, when we say co-interior, let's draw in the transversal for a minute so that we can all see it. I just want to make it a little bit more accurate. Pick it up and move it across. Is it moving? There it goes. There it is, like that. Very good. And what we're saying is, guys, this angle and this angle are between the parallel lines. Okay, I hope you can see that. They're between the parallel lines. We say they are co-interior. Now, they're not equal. No, they can't be equal. You can reason that out. But we can say that they add up to 180 degrees, and it's written down there. So we can give the reason as co-interior angles on parallel lines. Now, we can use these facts to not only show angles are equal, but we can also do the converse, the opposite reasoning, by saying if the angles are equal, or if the angles add up to 180, then we know they're parallel. Guys, there are two last little things that I want to just deal with, and that is triangles. Very quickly on triangles. What we can say is, you should all know this, that the sum of the angles of a triangle add up to 180, that the exterior angle of a triangle is equal to the two interior opposite angles. So the angle A and angle B is equal to C2. That angle there. Okay, C2. Make sure you know this. It's really important. You need to revise it. And I'm coming to the second to last thing now, is if two sides of a triangle are equal, then the angles opposite the sides are equal. So if these lines, which we show as double lines there, those two lines are equal, then we can say those two angles are equal. This is for an isosceles triangle, and we can refer to that as angles opposite equal sides. Got that? Very important for triangles. The last thing for triangles on this section is to say if two angles in the triangle are equal, then the opposite angles will be equal as well. So if we've got the angles equal, then we can say the opposite. We can say, now we know the sides are equal. Got it? Hope you have. Now, guys, I've just flown through some basic geometry revision. there's a whole lot more that you need to learn. You need to know about congruency as well. Now, I haven't got time to do that because I think you've deserved a bit of a break. But after the break, I'm pretty sure that I heard Dina's voice in the background, and she'll be here to take you through the rest of today's lesson. It's been my pleasure being with you. Make sure you join us next week because we're going to be able to give you a challenge question. And Itzai will be here to tell you about finding the mathematical genius in you. So don't miss out on that one. Grade 11s from me. It's been great being with you. Over to you.
Right, grade 11s, you've earned yourselves the right to a break, and we'll be back to this proudly sponsored by Macmillan Show. See you after the break. Welcome back, grade 11s. Hope you had a refreshing break. Dina's in the house. Pay attention to the lesson and you won't go wrong. Dina, over to you.
Teboho, teboho. Thanks a lot for the introduction, and yes, here I am, and very glad to be with everybody. And thank you to John, who just picked up on the basics of grade 8, 9, and 10 geometry. And we really did concentrate on congruent triangles in grade 9. And the notes are up on the link, if you can just go onto those notes just to get another look at it. I'm just going to go briefly through that because I want to really get onto the grade 11 geometry, all on the circles. So let's have a quick look at our triangles. If triangles are congruent, we get 4 different categories of congruent triangles, and that is if 3 sides are equal. So we will have side, side, side. If 3 sides are equal in 2 different triangles, they're congruent. We also can get the condition where we've got 2 sides and an included angle. We call that side angle side. And we've got the condition where we've got 2 angles and a corresponding side. In other words, the side is opposite the same angle in both triangles. So this side here would be equal to that side there. Okay. And then we've got the right angle hypotenuse side. And in terms of the circle geometry that we really want to focus on today, we need to look at the terminology, because that's really what we're going to concentrate on the next 2 weeks, is the various lines and areas that are formed by these lines. And the first one is that the radius is any line from the center to the circumference. We're also going to work a lot with the diameter. So this length here, that's really made up of 2 radii that are straight line. We are also going to deal a lot with the secant, which is a line that touches at one point. And then we're going to draw this line here, the chord, which is going to divide the circle into 2 segments. We're going to have a minor segment and a major segment. But this line is going to appear very, 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 very often, and that is the chord. The chord will have 2 points on the circumference. And in a moment, we'll see how important those 2 points are. But for now, if we focus on the radius, the diameter, we'll get to a secant later, and tangent, and the 2 segments that are made, that will be great. Again, there are notes to describe each of those points. We're going to look at the relationship between lines and angles, and the first one is, what do we mean by a subtended angle? And the best way to describe a subtended angle, there is a description of it, is just now we mentioned that a line that joins 2 points on the circumference is called a chord. If I had to take this chord and make it longer and longer and longer so it went through the center, we would then call that a diameter. And from this chord, if you take your fingers, you can create an angle at the center, and you can also create an angle at the circumference. So from those 2 points, I can make various different angles. And that relationship between the 2 points on the chord and the angle from where those 2 rays come from is what we call the word subtend. So an extremely new word, but a very powerful word because it tells us from which position the angles are being made. So I can make angles anywhere. I could make this angle over here. I could make an angle over there. These two blue angles are not subtended because they are sitting just inside the circle. But this angle over here at the center, we would say that it's subtended from that arc. So it's subtended by the center, and this angle would be subtended by the circumference. Okay, so the word subtends really means to create an angle at a particular position, either at the center or at the circumference. Now, angles in the actual circle don't have many relationships, but the ones at the center and the circumference do have a relationship. And I think that as some of you have been looking at that picture, you're wondering what that relationship might be. And we're going to look at the next slide to investigate what is the relationship between the angle at the center and the angle at the circumference. What is that relationship? Okay? I'm going to draw a circle. And remember, to subtend means I first have the position on the circumference. I'm going to choose 2 points on the circumference. And I'm going to subtend an angle at the center. I'm going to call that O. And I'm going to subtend an angle at the circumference. And I'm going to call that A. And if I call this angle X, then the angle that comes from the center, notice that I haven't changed the position on the circumference. It's the same position. So I'm not changing that to a new position and then subtending. It's coming from the same position, BC. So my arc hasn't changed. My chord hasn't changed, because a chord will subtend an angle at the center and it will subtend an angle at circumference. The relationship between A and O is that A will always be equal to a half of O, or in other words, angle O will be equal to twice angle A. So very powerful relationship that we're going to be using, and one of the first theorems that we're going to look at. Now you'll notice I've called it theorem 2, because theorem 1 is really a very basic theorem that we don't often use, and we will get to that at a later stage. But for now, I want to lay down the foundations with circle geometry. So the word subtend means that you're creating an angle that is created by pinning 2 positions on the circumference or on an arc, and that arc will subtend at the center, and that arc will subtend at the circumference as well. So the relationship, the first one, is that the angle at the center will always be the large one. However, this segment over here, this arc segment, is now subtending this center angle. And this segment is known, or this arc, is known as the minor arc. It subtends this angle of 2x, and it subtends this angle of x. And you'll notice that if this is maybe 50 degrees, then this one will be 100. And if this one is 60 degrees, then this one will be 120. So acute, obtuse, acute, obtuse, acute, obtuse, etc., being the minor arc. There is another arc on the circle, and that is this arc over here. And any angle that's subtended from a minor arc will have another major arc. So the blue one is the major arc. And that arc, we speak about subtending the angle that the minor arc does not subtend. So if the minor arc is subtending this obtuse angle, then the major arc is going to subtend the angle adjacent to that, which is that blue angle O2. And in other words, O2 will subtend a 360 minus 2x. So the next question is, if the white or if the yellow arc is subtending the yellow angle, then that means that that arc is now subtending angle A at the circumference. So minor arc, use your fingers with me, subtends center angle, back to the same position, subtends at the circumference. And the relationship is in a ratio of 1 to 2, angle and circumference. So the angle at circumference would subtend at the center, and if you go back to the same two positions on the minor arc, you would now subtend at the circumference. Notice I'm not going inside the circle, I'm going to the center and to the circumference. Now, the major arc is subtending the blue angle, which is the one adjacent to the 2x. So the next question is, where is this arc subtending an angle that is going to be half of that one at the center? And it subtends it into the opposite segment. So it subtends it into here. So this angle here will be half of the angle at the center, which is 360 minus 2x. Okay, let's have a look to see how that would work in a calculation. So we've got circle center C with points A, B, and D on the circumference. We've got some parallel lines. AD is parallel to DC, and AD is produced to E. D1 is 108, and we've got to calculate the size of the following angles. So we've got this angle over here is 108, and we've got this line is parallel to this line, and the question is to calculate angle A, C2, C1, and B. If this line is parallel to that, John went through earlier how parallel lines have got a special relationship if we draw the transversal, and that is that the corresponding angles are equal. So that would be 108. Now, when you write down the values of the various angles, you need to be able to provide an Euclidean reason. An Euclidean reason is the build-up of the various Euclidean axioms and theorems over the past a few years that you've been working with him. And so it's not sufficient just to be able to write an angle and say, well, that's just because it's that way. You need to give the reason as to what you've used. So in this case, we would say that angle A is equal to angle D1. We would give its value, and then next to it we would say, because AB is parallel to DC, and our corresponding angles on parallel lines will therefore be equal. So notice I'm providing a reason for that. Now, this angle on the circumference, this blue angle, is subtended by this arc DC, or DB. But DBs would subtend the angle C1. We need to find out which arc has subtended a circumference angle of 108. And that would be this big angle over here, which is this angle C2. So the pink angle would actually be double what that angle is. So that would be 206 carry 1, so it's 216. So the relationship between the center angle and the circumference angle will always be a 1:2 ratio. But because it's been the major arc that's subtended at circumference, we now can say that C2 is equal to twice of angle A, so it's equal to 216. And the reason that you would provide would be angle at center is 2 times angle at circumference. Okay, there's got to be that explanation that speaks about the theorem that deals with twice the ratio at the center to the circumference. And then finally, if you were going to work out angle C1, C1 just being in a revolution would just be 360 minus 216. So it would just be 360 minus 216, and that would be 144. So this angle here would be 144. And I think that's, yes, and then we could also work out angle B. By working inside the shape, you now have A, B, C, D. You could work out angle B by using your 2 angles you've already got in the triangle or in the quadrilateral, and you've got this angle here as well that you can work out. So 360 minus 108, and that would be 252. No, that's not 360. That's 180 because they're adjacent supplementary. Minus 108. That would be 72. So these two are adjacent supplementary. They lie on a straight line. And then this last one, we could now actually say that in a quadrilateral, they all add up to 360. So we're going to take away 108. We're going to take away 144. We're going to take away 72. And in the end, we're left with 36. So this angle over here would be 36 because of my quad. So notice that it's never, you can't ever leave the work you've done previously just in the other grades. You've got to always connect what are the lines doing, what's the relationship to those lines. So we had a pair of adjacent supplementary, plus we had the major arc subtending a major center angle, which subtends half of it at the circumference. And always reminding yourself that you need to have a reason, an Euclidean reason for what you're doing. You can't just say, oh, because I'm calculating the angle. You've got to have a valid geometric reason at calculating those angles. Let's just see if we can add something else onto it. Okay, let's add something else. What is the relationship between the diameter and the angle that subtends at the circle? So I've just worked with you with an angle at the center that is acute and is obtuse. But what happens if we have an angle, let's say of x, and I start opening up my radii, and I start opening up my radii? What happens is that at some stage, I'm going to get a diameter. And so the angle that's subtended at the center is actually this whole angle of 180. Now, if the relationship between the angle at the center and the circumference is a 1 to 2 relationship, then it must mean that at the circumference I'm going to be subtending a 90 degree. So the relationship between a diameter, there's my diameter, is that it subtends 180 degrees. It is a special kind of chord, subtending from the diameter. If I then go to the circumference, if that's 180, then my circumference angle must be half of that, which is 90. So there's a special relationship between the diameter and the angle that subtends at the circle. When we talk about at the circle, we mean at the circumference. So the angle at the circle equals 90 degrees when subtended by the diameter. And the way we would prove that we have a diameter is to show that a chord subtends 90 degrees. So we'll have a look at an example with that once we return back from Tebogo. Over to you, Tebogo.
It is now time for a quick, short break. If you feel you've missed something from this lesson, don't worry, as the notes are accessible from our Facebook page. We'll see you guys after the break. Welcome back, grade 11s. Please don't be shy. Post all your questions. We're waiting here to assist you take advantage of our presence. Well, without any further ado, we may continue with the show. Dina, over to you.
Thank you, Tebogo. And here we are, ready to go over once more what we've just done in the last section, and that is, what does the word subtend mean? And subtend is if you have two positions on the arc, and you're going to now from those positions meet either at the center or at the circumference. Okay. Now before the break, we spoke about point A and point B subtending an angle at the center, and that angle is being subtended. We can talk about two things really. We can talk about position AB forming the minor arc, because we've only taken a segment, a section of that arc, and they will subtend at the center. but they can also subtend at the circumference. Now I'm going to draw another picture. So I'm not going to draw it on the same diagram, but I'm going to draw one just for you to see the difference. If I was talking about position AB, but now using this arc as the major arc, subtending. The minor subtends the minor center angle. The major arc subtends the major angle at the circumference. And then the angle that will be half that will always be in the opposite direction. So it will be facing opposite that, and there it is. That's the major arc. Reason I'm doing this again is it's quite tricky to first try and internalize that word subtend firstly, and also where the position of the angles are. And the best way to see that is if you have the little arc will subtend the little angle at circumference, which will be the smaller angle at the center. So you see there are two angles. There's this angle here, which is much larger than that angle. So the small arc subtends small angle, the large arc subtends the large angle. So if I was to draw it on the same diagram, then I could say that this arc over here, big arc, big angle over here. The yellow, little angle at the circumference because it's coming from that little arc. And so play with that. Take various segments and find where those angles have been subtended. At the center, at the circumference. Okay, so we've got the angle at the center is twice the angle of circumference. And then just a little theorem is that if we have a diameter, then that diameter is going to subtend a 90-degree angle. Why? Because a diameter will have 180 degrees at the center, so when it subtends the circumference, it will be a 90 degree. So it's a special feature of the diameter. It will subtend a 90-degree angle. In this picture, we have some information with a given diameter, and straight away we can really just expand on that and say that therefore we have a 90 degrees, and we've got this line is parallel to that line, and we've also got that this line is perpendicular, BP is perpendicular to AC, and we've got that B is 35. Okay, what are the questions? We want to find angle A and angle C. Okay. Now, I'm sure some of you are already looking at this triangle over here and you're saying, well, if that angle's 90 and that angle's 35, then that angle over here has got to be 55. Okay? So that's angle C2. And while you're sitting on the parallel lines, you're traveling along the lines, and you're saying, okay, here's a little Z shape. So those lines are parallel, which means that the alternate angles will be equal to each other. So that is 55. Now, I'm really curious to see how you'd write that up, because it's one thing working on the picture. It's like a puzzle. You get given some information and then you build onto that information, and you can actually work very nicely. But part of your job is to write this up for an examiner who's going to be marking your work, or for a marker who's going to be marking your work. So remind yourself that it's one thing being able to really get excited and working out the puzzle. It's another one, it's another story altogether to actually write it all up. So we're now going to have to set this up and say, well, C2, I know, is 55 degrees because I have an angle sum, and there are two triangles in this picture, so we need to label angle sum in triangle DBC. Then we've got the special relationship of the alternate angles. Try and always write the angle that you're trying to find first, and try and write down the angle that it's equal to before you write its value, so that the examiner can see, or the marker can see, that relationship between the angles. And the reason is, always start with the parallel lines, AD parallel to CB, and then the kind of angles that you were working with. Don't just write down alternate angles, Because I can give you a diagram. Here's a diagram. The alternate angles are given, but they're not equal. What causes them to be equal is the fact that you have parallel lines. So if you just had to say alternate angles, that's not always true that they are equal. And so write down the parallel lines, because if you forget to write alternate angles, you'll still get the mark. But if you leave out the parallel lines, you may not get the mark. And then finally, what would angle C1 be? Here's angle C1. Well, I don't know C1 and I don't know angle D. And I know some of you are out there and you're putting up your hands and you say, yeah, you know how to work it out, because you've spotted that the fact that this diameter has been drawn, you haven't yet placed the 90 degrees. So it's important to just make sure that if you have a diameter, go to the picture with your fingers, move along that diameter, subtend, and automatically, what you've said earlier, put it on. Do not put on 90 degrees. Don't write it in. Mark off how 90 degrees looks like on your geometry picture. It's so much easier to pick up that these two angles are now complementary and that that angle over here is actually 35. And now that we've got that C1 is 35, I want to make a comment about CBD and CDA. You've done this in grade 9 before. What kind of triangles are these two because of the size of their angles? I'm sure some of you are shouting out and you're posting it on the page, right? You know that they are similar triangles. Why are they similar? Because the size of the angles are all the same. But you can see one is smaller than the other. The size of the sides is different, but the angles are the same. And so we call those similar triangles. How would we write up the C1? Well, the first thing we did was we made D 90 degrees. So D is 90 degrees. And the reason you use is just angle in semicircle. Because this is theorem 3, we have our own rule or our own reason for D being 90, or our own reason for angles subtended by the diameter. We don't have to, in this case, say angle at the center is twice the angle of circumference. Okay, and then the last thing we did was to work out the angle C1. And C1 is equal to 180, take away the sum of the other two, which is 90 plus 55, because we know that 3 angles in a triangle add up to 180 angle sum in triangle. And so C1 is therefore equal to 35. So notice, I've made a deduction, I've given a reason. This is what we call deductive geometry. I'm deducing something, I'm giving an Euclidean reason for it. And then I've used 180. Where does the 180 come from? Because it's the angle sum in the triangle that I'm in. And then I've used, and then I've calculated 35. So the reasons that we're giving are not by calculation or substitution. Those are not mathematical reasons. We are giving some specific reason because of the type of geometry that we are working with. Okay. Right, and then finally, let's see what the last theorem is for today. There will be a lot more next week. And that is a relationship between angles in the same segment. Okay. What do we mean by angles in the same segment? Remember, if you've forgotten what the rules are for the various names, just go back to your notes, is that a chord will divide the circle into the same segment. So we have, let's just create a circle. Okay, and I'm just going to draw the picture I had earlier, center and a little arc. Okay, and it subtends at the circumference. Okay, now this is a position AC. Let's just call that AC. You know that if I call this angle X, how much will the angle at the center be? Good, double that. If I had to now subtend in another place, from the same position AC, what would this angle be equal to? I haven't moved my center. I haven't moved my arc that I'm using is still this minor arc. So what do I subtend at the circumference? I'm going to subtend an x. Now, the fact that my arc AC has not changed, the blue angle and the yellow angle are both related to the center angle, means that they are the same. Now, there is a chord. I could have used it, but I didn't. But this chord separates this little segment from the big segment. And that's what we talk about when you say angles in the same segment. Those angles are positioned in the same region. They're both at the circumference. And they're not in the pink segment, they're in the major segment. They are both related to x. So my next question, how many angles can I draw in the same segment? Well, an infinite many. I can keep on drawing this picture. That's still x, that's still x. If this arc length does not change, then the size of my angles will not change. And that's what I say about angles in the same segment. So when we next use this very, very important theorem, we're just going to say angles in the same segment. Now, we can also have, because notice it's really about this arc length that hasn't changed. So if I have to create an arc length, let's say this arc length is the same as an arc length over here, if I choose the same arc length, and I subtend, then what I'm saying is that this angle and this angle will be the same, because my arc length that I've trimmed off the circumference is the same in both. So I can have separate arc lengths that are the same. They will subtend the same sized angles. So I can talk about equal chords or equal arcs subtend equal angles. So in this case, I haven't moved my arc length. I've created a whole number of angles. Here I moved my arc length, but I kept it the same length. Then I can still subtend equal angles. All right, and so just to go over that, let's just have a look at a picture that shows us that. And the best thing about doing circle geometry is to focus on a point on the circumference and use your fingers. Where does it come from? Okay, it comes from here, from CD. So 70 degrees comes from CD. Can you find another angle that DC subtends? So that would be coming from this arc length DC. With your fingers, does it subtend anywhere else? Yes, it subtends to A2. So this will also be equal to 70 degrees. Okay, go to another position on the circle, B1. Where does it come from? From AD. So let's color that in pink. There and there. Where does that come from? From AD. Can you find another angle that AD subtends? Let's go find it. Let's travel along it. There we go. Oh, and it just disappeared. So let's go back and find it. Okay. There it is. Okay. So AD subtends all the way to C. We were traveling along there. So that angle will equal to that angle. Okay, so as long as you can find angles on the circumference that are subtended from the same arc, then those angles will be equal to each other. And we had to show that A1 was equal to A2, where BC was equal to DC. So BC was equal to DC. What kind of a triangle have we got here? This triangle over here. What kind of triangle? Oh, I hear lots of people shouting. You're saying isosceles. So therefore, angle D2 is also equal to 70 degrees. Now, this 70 degrees comes from BC, which is also subtended by A1. So therefore, A1 is also equal to 70 degrees. Okay, so thank you, everybody. That's the first 3 basic ideas of circle geometry. We will be back again next week with a lot more of circle geometry.
Thank you so much, you guys. I'm just going to read a few posts that I've been getting from a few mindsetters. Augustine says she's enjoying the show. Priska says she loves the complex lesson. And then I got one that says, Dina, you're the best math teacher ever. Hope to see you again. And that's from Kiabezwi. And then one last one is from Neo, and he says, thank you so much, Dina. You help us a lot. And I'm sure he speaks on behalf of all the mindsetters. Thank you. A big thank you to my Macmillan for proudly sponsoring the show. And thank you guys for allowing Team Mindset into your homes. Until next time, goodbye.